These are the notes on gravity. We've already talked about some of the events in the development of our universe. Inflation, followed by continued expansion right to this day. We know this because of, among other things, the redshifts of distant galaxies, showing that they once were a lot closer to us, meaning that the universe was a lot smaller, plus the leftover heat seen in the cosmic background radiation. But what is going to determine the future of our universe has a lot to do with gravity, also known as universal gravitation. Gravity was quote unquote discovered by Isaac Newton. Well, actually, people had been experimenting with it before then, obviously, like Galileo and just anyone who ever dropped something, I guess. It was just Isaac Newton that connected the gravity we feel here on Earth to the gravity between the Earth and the Moon, and between the Earth and the Sun, and between any object. He realized that it was all the same thing. He formulated his famous equation that we are going to use in our new assignment, and it is F, which is the force of gravity, is equal to G, the big G, which is the universal gravitational constant, multiplied by the two masses. The two objects, the mass of each object multiplied together and divided by the distance between them squared. Now that is important because gravity diminishes, it's divided by the distance between the objects squared. So when objects get twice as far apart, the gravity doesn't divide by 2, it divides by 2 squared, it divides by 4. When objects move 10 times farther apart, you don't divide the force of gravity by 10, you divide it by 10 squared, which is 100. So gravity is very concentrated near the object and it drops away rapidly. However, it does extend, theoretically, forever. There is no limit to the extent of the gravitational force, although eventually it gets very, very, very weak, very minor. So gravitational force decreases with the greater distance. The farther away you are, the weaker it is. It depends on the mass of the object. The greater the mass of an object, the greater its gravitational force. So a lot of people think because everything falls at the same acceleration here on Earth that everything is feeling the same force of gravity. No, that is not true. A larger, more massive object does experience a greater force of gravity. The only problem is it's harder to move a more massive object. It has more inertia. So that exactly compensates for that. And that's why everything falls at the same rate in, let's say, Earth's gravitational field. So a more massive object does experience a greater force of gravity. Now, at the bottom it says, note, Einstein later showed in general relativity that gravitation is caused by the warping of space around masses. How did he prove this? He proved this by things that would only happen if the space itself was warped, and it wasn't just a gravitational attraction, a force between two objects. He showed that even light was affected by gravitational impressions in the universe. So light should not be affected by gravity under this equation because light has no mass. But Einstein shows that it did. So there are a few things that this equation won't get you through, but for the most part, it's pretty good at predicting the force of gravity between any two objects, as long as you know the mass of each object and the distance between them. So let's take a closer look at Newton's equation for universal gravitation. F, which is the force of gravity, is equal to the universal gravitational constant, the big G, multiplied by the mass of one object times the mass of the second object, divided by the distance between them squared, r squared. The gravitational constant, the big G, is 6.674 times 10 to the negative 11 meters cubed per kilogram second squared. Now, is that a big number or a small number? It is a small number. So small numbers don't usually make much difference unless they are multiplied in. If you were adding a small number like that, it wouldn't make much difference, but we are multiplying it in, so it has a huge effect. What is a meter cubed per kilogram second squared? I wouldn't boggle your mind with that. It's just one of those things that constants get. Constants get weird units, and that's because those units are designed to cancel out when you get your final answer. So when you get your final answer, well, those units should make sense. The units of force you will get over there will be in newtons, but in the meantime, you're going to have weird units along the way. The other thing it's important to remember when it comes to universal gravitation is that there is a force between any two objects of any masses, no matter how large or small or how far apart they are. So sometimes we don't consider this because there is gravity between myself and a pencil, between two students that are seated at the table next to each other. There's gravity between all of these things. Like in the example that I give you in the calculations, between a bowling ball and a billiard ball, well, there's gravity between those. However, it's very, very minuscule when compared to the gravity we're feeling from the Earth, so we don't usually notice it at all, really, but it does exist. It's important to realize that there is gravity between any two masses, no matter how far apart they are. So gravity is what brings us together today. Gravity exists throughout the whole universe, between any two galaxies. So imagine that. Between any two distant galaxies, there is gravity pulling on them, pushing them toward each other. Well, maybe not, but maybe slowing them down. So what's going to happen to our universe? We've known for a long time that there were really only two options for the future of the universe. There's really only two possible paths. One is that the universe will just expand forever, just keep on expanding and expanding and expanding, and eventually what will happen is we will no longer even see other galaxies, and the universe will cool off, and they call that the thermodynamic death of the universe. It sounds kind of sad, but don't worry, it would take a very long time, something like 100 billion years, so I wouldn't worry too much about that future. The other option is, though, what if there is enough gravity? What if there's enough mass in the universe and they're still close enough together, the masses are still close enough to each other that there's enough gravity between them to actually slow this expansion? If that were to happen, it turns out there is no possibility that the universe could just stop expanding and stay like that, because gravity would continue to pull the galaxies, any masses, closer together. And then they would get closer together, gravity would increase. As they got closer, it would accelerate. They would be pulled in faster and faster, and then they would collapse. And that is what we call the Big Crunch. That has been hypothesized for many years as sort of the exact opposite of the Big Bang. And yes, again, it has a funny name, the Big Crunch. But now, guess what? The evidence has rolled in, and over the past decade, we've pretty much figured out which option is going to happen. We know how much mass there is in the universe, even though we don't know what all of it really is. There's what we call dark matter, but we can still measure its mass. And based on what we know now, it's almost, I would say almost decisive that option number 1 is what we can expect for the future of our universe. The universe will expand forever, because not only is the universe not slowing down enough to ever stop expanding and collapse, no, not only that, it's actually accelerating its expansion again. And we're not sure why. They call this dark energy, whatever is making the universe inflate again, so to speak, not quite as dramatic percentage-wise as the original inflation we talked about right after the Big Bang, but it is accelerating. The universe is now expanding faster and faster. So that clearly means that gravity is not doing its job. There's not going to be enough gravity to slow it down and stop it if it's actually speeding up. So it's pretty much known, not 100%, but evidence is stacking up that the universe will expand forever and never collapse. If the universe did collapse and you were to look around you, every galaxy you saw would be blue shifted. It would be a very, very different situation. So if we found ourselves in that kind of universe, we would talk about the contraction of the universe, not the expansion. Interesting. So those are the end of the notes on gravity. However, you still want to watch my gravity calculation examples because I do a calculation just like the ones you do on the new assignment. Okay, so please watch. These notes were kind of short, and I did that deliberately so you would have enough time to watch my gravity calculation example, which is a separate video. And that shows you how to do those calculations. Now, you might not have a good sense of what the numbers mean when you get your answers, but you can sort of see how they compare to each other. Just look at the exponent, 10 to what power? That sort of gives you the sense of how much gravity is between two objects. And then compare it to the other example, all the problems that you're solving. You can see, oh, that one is hundreds of times more, that one is millions of times more, that sort of thing. Okay? So watch the gravity calculation examples now.